Hello everyone, Interpretable Zero-Shot Learning for Sensor-Based Human Activity Recognition. The introduction. Human activity recognition is the act of identifying the activity a human is doing, like walking, sitting, and jumping, by using monitored data. And we use human activity recognition in many fields like medical applications, for example, elderly care, smart home systems, and surveillance. And currently, there are many deep learning approaches for this task, but majority of them are based on visual data like videos and pictures. But nowadays, the use of wearable devices like smartwatches are becoming more common, and these devices collect a multitude of sensor data continuously, which we can use to recognize the user's activity. These sensor data are called inertial measurement unit data, and these data are time series in nature, and this data reports on body movements using forces, angular rate, and sometimes the orientation of the body. Collecting and annotating large amounts of these sensor data for a lot of activities is expensive and time-consuming. Because of this reason currently available, public sensor datasets only contain data for limited number of activities. And because of this, even though we can train human activity recognition for these available activities, it is hard to extend them to a wider array of activities. This is where zero-shot learning comes into picture. Many of these human activities like running, sitting down, climbing can be broken down into common attributes. For example, if we look at the figure, we can see that arm curl is common attribute for both bench dips and upright row. Now, if we train a human activity recognition model on bench dips and upright row data, using these auxiliary information of attributes, we can then use this attributes to map a relationship between a trained activities and untrained activities, like dumbbell side raises in this example, so we can also predict that activity without training it specifically. This strategy is known as zero-shot learning, and this helps the limited data problem. But the major key factor is the auxiliary information required to use this strategy. Currently, majority of zero-shot learning work use text labels like these as auxiliary information. But video data seems like a better alternative for auxiliary information. Why? Because videos are readily available, and unlike the text attributes earlier, we don't need an expert knowledge to create them. But there is also a few disadvantages of using videos as well, it being that for human activity, recognition background information is not required and might confuse the model, and also processing videos take a considerably long time. Another important factor when considering human activity recognition is interpretability. It is important to know how and why a model gave a specific output to an input to build trust on that model. For example, if we take an elderly monitoring system, we can use human activity recognition to identify abnormal behavior. If so, then the caretakers might need to understand why the model has classified as abnormal behavior. This provides insight into the problem. Since human activity recognition deals with sensitive tasks, it is important to extend our work that we create to be able to explain its output. But currently, majority of explanation methods used rank the importance of input feature. This is not intuitive for general people. So our task in this research is to build an inherently interpretable zero-shot learning model with videos as auxiliary data, but improving accuracy and latency of the model by removing the limitations of video data that I mentioned previously, by extracting the movement and also introducing an intuitive explanation for the model outputs. The research objectives here are: introduce temporal modeling to leverage inherent IMU nature in IMU-based ZSL human activity recognition. Develop an inherently interpretable ZSL HAR model using videos as auxiliary data. Introduce a new, more readily understandable explainability method and related evaluation schema. Literature review. Here, filtered high-impact studies and summarized all into comparative table of related studies, as it evidenced that none of the ZSL HAR researches were incorporating time series modeling. None of the ZSL HAR-related studies are inherently interpretable. Research methodology. The first novelty, TESRNet, Temporal Zero-Shot Activity Recognition Network. IMU data-based ZS-HAR model using videos as auxiliary data. Introduces IMU encoder that exploits temporal information of IMU signals. introduces KNN-based inference method to tackle the instability in ZSL performance and reproducibility in ZSL. High-level intuition. The feature vector here basically works as a semantic representation of a respective action class, mimicking the class label in the supervised setting. IMU encoder's job is to generate the semantic representation of a specific human action class, given an IMU signal sample, and an I3D video encoder that generates the base semantic representation vector for each class based on video data. IMU encoder trains to generate accurate semantic representation from the IMU signal, while the pre-trained I3D video encoder aims to generate an accurate and generic representation for a class based on the videos that it gets. In training first, we put the IMU sample into IMU encoder and get the feature vector. We then put videos related to the IMU sample class into I3D video encoder, which generates the latent embeddings. We then create a semantic representation for each class using these latent embeddings by getting the average of all the embeddings of that specific class. We calculate the L1 loss, coined matching loss, using the class semantic representation and feature vector. This is done to make IMU feature output resemble the semantic vector generated by the I3D video encoder model. We use a similarity score such as cosine similarity to get the predicted class from the feature vector and use that output to calculate the cross-entropy loss coined as classification loss. We use a weighted combination of these two losses to backpropagate over both models to update their weights. Our main idea is to use the semantic class representation, just like previously using the I3D model and the feature vector generated by the IMU encoder, to get the class of the IMU signal. For this, we use a novel KNN-based approach that not only improves the results, but also improves reproducibility, which is a severe problem in ZSL models. Unseen action class inference phase. We generate the class semantic representation like previously during training for all unseen classes using the I3D encoder. Then we get an IMU sample related to one of the unseen classes, and generate the feature vector using the trained IMU encoder. Now we use the generated class semantic representation to set the neighborhood in the KNN algorithm. Finally, we use the bested neighborhood KNN algorithm with the feature vector, which will give the corresponding output for the generated feature vector. The second novelty. Says Harn, Self-Explainable Zero-Shot Human Activity Recognition Network. Integrates self-explainability with ZSL modeling in the fields of IMU-base HAR. Introduce readily understandable explainability method using skeleton figure videos. Design novel model explainability evaluation schemas. 1. Dynamic time warping-based movement, similarity scoring. 2. Discrete Frechet, index-based movement authenticity analysis. Here we keep the same IMU encoder architecture and video encoder from the previous TensorNet model, but here we add a skeleton decoder that we modified to integrate explainability through the generation of human skeleton movement seen by the IMU encoder. First, we create a skeleton movement dataset by sending the videos through the pose extraction modules to get the joint position locations in the videos. We use the video data to generate the class semantic vectors using the semantic vector generator unit, which will be discussed in the next slide. We use these class semantic vectors to train the IMU encoder and the skeleton decoder as well. To calculate a matching loss and classification loss, we employ the same methods we used in the previous model, but in addition, we also calculate two new losses by calculating the L1 loss between skeleton reconstruction of the skeleton decoder using the IMU feature and calculating the L1 loss between skeleton reconstruction of the skeleton decoder using the I3D video vector against the pose extracted skeleton. The combined loss is coined reconstruction loss and is used to train the skeleton decoder. During the inference state, we use the semantic vector generation unit to generate the class semantic vectors of the unseen classes. If you look to the left, you can see the semantic vector generation unit in detail, which consists of a video encoder model to get the feature vectors of the videos and the average the videos of a specific class to get that class's semantic vector. We use the trained IMU encoder to get the feature vector of the IMU signal like the previous model, and we then use a similarity measure like cosine similarity to get the most similar class. Afterwards, we also feed the feature vector to the skeleton decoder to get the skeleton movement video. Research experiments and results. We experimented on 4 IMU datasets, which are extensively used for HAR benchmarks and ZSL-HAR benchmarks. Notably, PAMAP2 works as baseline dataset due to almost all ZSL-HAR studies experimented on this dataset. However, these 4 datasets have significant variation in characteristics, from the number of subjects that used in the collection process to hash IMU sensor. Also, the human action complexity recorded varies from knee bending to car driving. Before utilizing the IMU signals in our models, we carried out several pre-processing steps. Firstly, we addressed missing values, NaN, in the datasets by employing linear interpolation. Next, we focused solely on the features associated with IMU signals and discarded irrelevant ones. Additionally, we resampled the signal to account for variations in data recording frequencies across different IMU sensors. To enhance the quality of the IMU signal, we applied a smoothing technique to reduce noise. Moreover, we employed windowing with overlapping to generate samples, allowing for a more comprehensive analysis. To ensure proper evaluation, we separated the samples of seen and unseen classes. This separation allows us to assess the model's performance on both familiar and unfamiliar classes. Finally, we created a validation set specifically from the seen classes. We used a 10/90ths holdout ratio, where 10% of the data was reserved for validation purposes, while the remaining 90% was used for training. For the needed video data in our modeling, we collect videos from public dataset and public websites. Only one previous research has studied about video-based semantic space before, like what we do here, but they haven't released their video dataset publicly. Therefore, we build 4 separate video dataset that matches with action classes in the 4 IMU datasets we use for our experiments. We collect video clips from HAR video-based datasets such as HMDB51 and NTURGB120. Also, from websites like Pixar.com, YouTube, we collected especially for human action classes for which videos are really rare, such as Nordic walking. Training run in 5-fold setting, where to get unseen performance for all the classes. All action classes separate into 5 disjoint sets, and named those classes as unseen class at each fold, and put remaining classes into seen classes at each fold. We record the accuracy, precision, recall, and F1 score for both training and test time for each fold, and we record the performance in training time specifically to understand whether model trained correctly, and check for underfitting and overfittings. Finally, from the unseen accuracy value collected over 5 folds, calculated final model performance metrics average accuracy per class, as defined in the equation. Model benchmarking emphatically shown that unseen performance as defined early in both of our introduced models are outperformed, their predecessor model by significant margin. More importantly, the result elaborate the proposing model performs consistently better over all 4 dataset. Even the dataset varies a lot, as we discussed. Here you could see the model explanation generated by the SEE-Harn model across 4 datasets. Thank you.